In the last few videos, we were discussing about the characteristics of SER, that is a static array of SER. So this is a static array. It's a graph between VA and IA, and this is a structure of SER. And we have learned the gate triggering method. When you apply voltage, that's the most efficient technique. When you apply voltage between gate and cathode, you can easily trigger SER. That's called gate triggering. But in the static characteristics, we have never mentioned about the time, which means after the application of this gate voltage, how long the SER will take to turn on, how much time it will take to turn on, what is the turn on time of SER. Similarly, once the current has fallen beyond the holding current, how much time it will take to turn off the SER. So what is the turn on time of the SER, what is the turn off time of SER, we have not specified in static characteristics. So all those things like the turn on characteristics and what is the turn off behavior, how much time it will take, all those things will be discussed in this switching characteristics of SER. Okay, so today we will learn about the switching characteristics of SER. The purpose of the switching characteristics is we have this SER structure PN. So this is anode and this is cathode, gate. So I am going to apply voltage, gate voltage across gate and cathode to turn on this SER. When I apply that gate voltage, what happens to anode voltage, what happens to anode current, what happens to the gate current, how much time will the SER take to turn on, will it turn on instantaneously or will it take some microseconds. Similarly, what is the turn off time of the SER, will it turn off instantaneously or will it take some time, what is happening inside these 4 layers during this turn on and turn off process, those will be discussed in the switching characteristics. So this switching array is actually called the transient array, because at the instant of turn on what is happening, or at the instant of turn off what is happening, that is called transient. Earlier we have learned this characteristic, this is called the steady state characteristics. After you have applied the gate current after a long time, what is the steady state behavior of SER, that is called the steady state array. This characteristics is called the transient array. So based on that I will be explaining this transient characteristics. So you have supplied a gate voltage VG, I am going to supply a pulse gate. This VG is going to be a pulse, I am going to give a pulse. VG is a pulse voltage. When you supply this, what is the nature of IG, what happens to VA anode voltage and what happens to anode current, that will be discussed. First I will draw the turn on characteristics. So it's a graph, you have to draw all these things, you have to draw your gate voltage that you have supplied. Okay, based on the gate voltage, what is the nature of anode current, what is the nature of this anode current, what is the nature of anode voltage, or you can draw here anode voltage and this is anode current. Okay, what happens to, what about the power loss during the turn on time. So initially, as I have said earlier, I am going to supply a pulse between gate and cathode. So this is a pulse. Okay, so this is gate pulse. Thing is that you are going to supply pulse between PN layer, this is PN layer, so you are going to supply a pulse between this gate and cathode, that's the meaning. Okay, so when you supply the gate pulse, what happens to the gate current, IG, this is IG, between gate and cathode, when you supply, what happens to IG, will IG also be a pulse or will IG will take some time to rise. So this is a shape of IG gradually increases linearly and finally you will get the steady state value of IG. So this is IG, the gate current. Okay, so the gate current slowly increases and I'm going to mark this. This is almost 90% of Ig is reached at this point, so I'll be marking this as 0.9 Ig or 90% of Ig, and this is the 100% of Ig. So when the gate current reaches 100% of Ig, what happens to anode current? So anode current, when the gate current has reached 90%, anode current slowly start to increase, and it rises linearly, and after a long time, when the gate current has reached its final value, okay, anode current will take some time, and finally anode current reaches its steady state value, slowly rises, and finally it reaches its steady state value. Okay, so this is anode current Ia. So I'm going to mark this is anode current just start to rise, so I can mark this as 10% of Ia or 0.1 Ia, and this is almost 90% of Ia or 0.9 Ia, and this is 100% of Ia. Okay, so this time is divided to 3 different intervals. The first time the anode current is just start to rise, this is called the delay time Td, and this is anode current rises, so this is called Tr or rise time, and finally from 90% to 100% again it takes some time, so this is called spread time Tp. So the total turn on time is the sum of Td plus Tr plus Tp. So this is the total turn on time of SCR. It will take around 1 to 3 microsecond or 1 to 4 microsecond for the SCR to turn on. So the idea is very simple. You supplied a gate pulse. This is a pulse voltage. Slowly the gate current increases. Once the gate current has reached 90%, anode current start to flow. This is anode current. So I am drawing again PN structure, gate and cathode. So between gate and cathode you have supplied a pulse. This is the pulse that I have drawn here. So gate current slowly increases, so this is Ig. Once the gate current has reached 90% of its value, anode current slowly increases from anode to cathode, so this is the step. So it takes a delay, so that time is called delay time. And after that what is happening, what is going to happen is that actually there is some correction. Anode current slowly start to increase, and this is actually 0.10% Ia. This value is 0.10% Ia. From this anode current slowly increases, so this time is called delay rise time. And from this 90% of Ia to final Ia, again it takes some time called spread time. So the total turn on time is 1 to 4 microsecond. So what happens to anode voltage during this time? So we all know that SCR has turned on. From when a current rises from its zeroth value to its final value, we know that switch is on. So what happens to anode voltage is normally the voltage across the switch also going to reduce. Okay, so this is a 0.9 or 10% of Ia. So if you draw this, the anode voltage initially it was Va. When the current just about to rise, anode voltage slowly decreases. This is 90% of voltage or 0.9 value of Va, and when the anode current has reaches 90%, the anode voltage drops to 10% or 0.1 Ia, and finally when it has reached the full value of Ia, anode voltage also reduce almost to zero. It's the on state drop. Okay, so this is the value of anode. Now you go to the textbook and learn about this Td, Tr and Tp, and what's the meaning of Td, Tr and Tp. Anyway, the idea is very simple. The turn on time is Td plus Tr plus Tp. It will take some time. It is 1 to 4 microsecond. So this is actually the turn on characteristics. When you give the input voltage, this is actually going to happen in SCR.